What's up, guys? Welcome back to Vanover Machine and Repair, and welcome back to the brand new beautiful Lion lathe. If you want to see more about this machine, check out the first couple videos we have done where we brought the machine in, and in the second video we talked about the tooling and the tool post, and we're continuing on with that theme. And this video is going to be focused on upgrades or changes that we're going to make to the machine. And it will probably be a several part series where we make some modifications to make this machine suit our use cases a little bit better. So with that being said, let me bring you in close, show you some of the problems and some of the solutions that we're going to be tackling on this brand new machine. Before we hop into the actual modifications, I want to address the elephant in the room, and that is, why in the heck would you buy a brand new machine and start tearing into it to make changes and modifications? That's a valid question, and for most people it'd be completely unnecessary. But I'm very particular about my machines, and this machine is 90 to 95% where I think it needs to be, but I want to dial in that last 5 to 10% for what we're going to be doing here in this shop specifically. It's going to make my user experience even better, and hopefully it's going to allow the machine to last longer and wear just a little bit less than it would as it currently sits, and that's why we're going down this path. In no particular order, we're going to start with the tailstock, and I'm just going to give you an overview of all the things that I would like to change, and I'm not really sure which things we're going to do first. It all depends on parts availability and my time here in the shop, but I'll give you a brief overview just so you can see where we're going with this. So this tailstock, first and foremost, this tailstock is a dream to operate. Having the 2-speed option, man, it is so nice, especially drilling grease holes, long deep holes with long skinny drill bits that are like 6 to 10 times the length of the diameter. Putting it in a less aggressive feed really prevents me from breaking drill bits, and it allows me to have much finer control. So that feature on this machine is probably one of my top features. Now the thing that we're going to be addressing is this tailstock is rather heavy. Now I'm pretty small, 130 pounds, soaking wet, and I can move this thing, right? But it takes, it takes a fair amount of force to move. Once it's going, it goes pretty good. All right, part of that is because it's heavy. The other part of that is just a lubrication thing. Obviously, I could kind of slip this up and lubricate under it, and it would definitely get easier, but I think the surface on the bottom of the tailstock is ground, as is the bed, obviously, and we have a lot of stiction there. So there's a couple ways to address that, ideally, in terms of adding a pressurized oiling system, but that probably isn't going to happen on this machine just due to time. But what we are going to do is we are going to figure out a way to add a handle or a rack. That way we can move this tailstock nice and easy. My American has one, and I've been talking back and forth with Johnny. It seems like we might be able to get a couple parts together, and we'll be able to move this very nice and easy. Now, I have heard your comments. Multiple people have told me, just get this attached to the actual carriage and power it with that. That is a good idea, but that is a bad idea in terms of convenience, at least in terms of speed, right? If every time we wanted to move this tailstock, we were reliant on the carriage, that wouldn't be very good. Now in certain circumstances, yes, you can use the carriage to move this, but there's a lot of scenarios where this is fixed. Maybe it's over there and it needs to stay over there, and you want to be able to move this from the back to the middle, and you don't want to traverse all the way down because you need to leave this as a location. Moving right along, you can see that we've already addressed one of my frustrations with the machine, and that is this chip guard. We've removed it, and we've installed the limit switch permanently so we don't have any issues, and I have not looked back since. I feel much more comfortable using the machine, and everything feels a lot more natural and even safe for me, being able to access the chuck and to be able to put some tooling up here and just not be as cramped with that guard in the way. But by removing that guard, we do lose one feature that is important, and that is coolant containment. I thought about a lot of different ways to do it. Some of you guys even suggested taking this and sliding it back even further when it's not in use. But the reality is, even with this slid back further, it still kind of blocks this area which you use quite frequently. And really, I think the best solution would be to have a chip guard that's hinged at the back, like is on some lathes. So when it's out of the way, it doesn't impede this area. But when you need to pull it down for certain operations, you can do so. However, I realized that we already have a really nice shield, and that is in the form of this one that comes on the compound. So what we did is we reinstalled the bracket, and then I machined up this knurled pin that allows me to put this on and off the machine nice and quickly. Before it was installed, it could come off, you know, in maybe 3 minutes, but now I can take this on and off much quicker than that, and we can use it when we're doing drilling by taking the top slide and carriage and advancing it over. So this blocks the coolant, or if I want to do any machining, I can use this. And then when I'm done, all I do is pull this pin and I can set this out of the way. That allows me to have an open layout for the machine, but also when I need it, I can have some sort of coolant protection. Continuing on with the coolant theme, we did end up adding this modification to give us an extended reach coolant feed and a second valve on the back, and that is, as I mentioned before, version 1, but I would like to upgrade even version 1 to version 2 and make it a little bit more effective. So the main issue with this is twofold. One, this is within the diameter of the swing on the lathe, meaning it's less than 25 inches. So if we were to turn a 25-inch part, we would actually contact both of these. Now, several of you mentioned that that's not likely to happen because the cross slide only has a 17-inch swing, and that's true using conventional wisdom. However, we do a lot of impellers here, and a lot of times the impeller may sit in this area behind the top slide, and the smaller shaft will be obviously in the chuck. And in that case, you can run up to full inch, 25-inch diameters, and if that's the case, you're going to contact both of these. So long term, I would like to make an extension bracket that gets both of these things back a little bit further, so that's not an issue. And when we go to do that, I would like to redo this with a solid stainless billet piece that's more rigid, less floppy, and has more coolant ports. Just a little bit cleaner. It's not something we're going to address right now because this does work, but it's something we're going to be doing down the road. The other problem with this setup is on the bottom of this, there is a 90-degree plastic nipple that attaches to a hose. That's fine, but the hose for the coolant feed basically just lays down in the chip tray or around that area, and I've had several times where I move this carriage side to side and that hose gets caught because the hose isn't inside of a cable tray or routed properly. It can easily snag. So I want to address that, and I think we'll be able to address that when we adjust the cable tray on the front of the machine. We briefly touched on this in the other video, but we have several problems here that I think we're going to be able to solve with the same fix, and that is a couple things. One, this chip tray is pretty thin and flimsy, number one. Number two, it doesn't hold a lot of chips, which is a problem because we're going to do a lot of work on this machine. And number three, we have limited coolant capabilities in terms of the coolant capacity. So what we're going to do is we're going to make a custom chip pan coolant tank that is an all-in-one assembly, and that's going to allow us to have increased chip storage and also increased coolant capacity, and hopefully add a second drain port so that the coolant can drain back and recycle quicker. And we can also run a larger coolant pump so we can get a little bit more flow. The other reason why I want to do this is I have some folks that come in and clean out some of the machines, and on some of the other machines they can just reach down and clean out the chip trays if they have them, or on the floor sweep them up into a barrel. But on this machine it's designed to be serviced from the rear, and that makes having someone come and clean up, it just makes their life difficult. Immediately, I removed that front cover, which does allow these trays to be pulled out from the front, but this carriage needs to be all the way down to get both trays out, because these chip trays will hit this cable tray. This front one can come out right now as this is, but the back one cannot. So by making a custom chip tray, we can have one that's on wheels, so it'll slide nice and easy, and it will be able to allow them to just pull it out with zero skill and having to turn on the machine, and be able to empty out the chip tray a little bit more efficiently. It will also just give us more capacity, because right now when I run coolant, like if I'm doing a lot of drilling, I can easily deplete the only 18 gallons of coolant, and I really do need more coolant so that I can run more continuously. So that'll kind of solve all those problems. But in order to make that happen, we need to eliminate this or adjust it so that way it's not in the way. And the main issue here is this one here. Right now, as the way this is designed, this chip tray comes out above it, but if we make a large container basically on wheels, it's gonna hit this. So I went back and forth on how to do this, and I think what I'm gonna do is I'm gonna make a compromise. Instead of moving this whole thing to the rear and redoing all the wiring, what we realized is we can actually just cut this here, and we can run the wiring through the casting and eliminate this lower bar here. And that'll just allow us to have full access, at least in this first chip tray, for a full-sized tank tray combination. So the first thing we're gonna do in terms of projects is we're gonna be relocating this front piece of the cable tray through the casting so that we have full access for a custom tray here on the front. And the last modification we're going to be doing for now is adding a one-shot oiling system. Now this machine does come with an oil pump in the apron, and it does work very well. It provides tons of oil to the waste surfaces, which is the most critical. However, it does not provide any oiling to the nut or to the top here where the top slide rides. And anyone who operates a lathe long term knows that the part that wears on these lathes the most is this top slide. So by adding a pressurized oiling system to the top slide only, it's going to allow us to increase the service life of the top slide, and more importantly, it's going to allow the top slide to run nice and wet on way oil and flush out any coolant that seeps its way into the top slide, which can be a problem, especially running tons of coolant on this machine. So that is not necessary at all, but I do have it on my other American pacemaker, and I really, really like it. It allows the machine to run nice and wet in this area, and you can just tell a difference in operating the cross slide and how nice it operates. So since we need to relocate some of the wiring anyway through this area, it's going to be a perfect opportunity to take this apart, to inspect it, to see how good the scraping is. If we need to make any adjustments, we'll do that at that point. We'll add our oiling ports, and then we'll be able to run our coolant line and our oiling lines back through the top of this top slide and down back to the cable tray. So we can kind of do all of the modifications simultaneously and make sure all the wires and all the air and all the coolant is hidden inside of the cable tray and nice and clean, which will make this machine more enjoyable to use and last for many years to come. With all that talking out of the way, it's time to get to work. We're going to start with the path of least resistance, and that is working on the cable tray. I have a couple big jobs right now in the shop, and I don't want to fully disassemble this machine and regret it, but I do have a couple free days, so we're going to tackle the electrical first. Once we get that done, I can make the coolant tray outside of the machine so we don't have to down the machine. And then when I have a little bit more time, maybe in the next month, where we can down the machine, we'll take the top slide off and do the oiling system modification. So we're going to start by removing this front cable tray and see where we're at from there. The idea is just to take these wires, I'm going to be labeling them and disconnecting them back at the box. And then we're going to drill a hole here, cut this, and we're going to drill a hole here and then run them back through the casting. And that should be pretty straightforward. We'll modify this cover to lay it on to keep the chips out, and that should actually work out real nice. We need to move this box out of the way to access that flexible conduit. And I think, if I'm looking at this right, this box is actually on hinges, which would be really, really cool. I think we remove this nut, or bolt rather, and we slide the whole thing to the side, which would be really nice. Wow, look at that. Nice work, Lion, nice work. I gotta take these two flatheads off. And we're trying to access this, and I believe the clutch adjustment is here. I wonder if there's some screws behind this cover maybe. There we go. Now this should come out. I just kind of got in here and cut some zip ties back there, and these are the wires in that cable tray. So basically what I'm going to do is I'm going to figure out which wires in this flexible conduit come out into the box. I will mark them and then fish them back through, and we'll start by relocating those guys. I've isolated the wires to these 5 groups. I'm not exactly sure which wires go where, but I've marked each group with some nail polish, and the wires are labeled. So I'm going to pull them out and carefully just confirm the labels are in the right spot, and then we'll fish those through the conduit and then back at the other side. It's going to be fairly tedious, so I'll meet you over at the other side once I get these detached and we're ready to fish them through the casting. Next step is to drill a hole here in the foot. I was originally going to run these wires through the casting on the bed, but the casting on this Lion lathe isn't hollow like my other one. It's mostly solid, so there really isn't any good routing. Luckily, this foot is hollow, however, so we'll put a hole here, we'll put a hole on the other side, and we'll run the wires along the base. This is a really good application for anchor lube. I've drilled a ton of holes in cast iron making modifications, and it works really good to just keep the bit lubricated and allow us to get through there rather efficiently. I'm drilling this hole oversized so we have some room for coolant hose and my oil line. Get some lube in there. Once we get started, it'll be a little less hairy. This is a carbide hole saw too, which good and bad at the same time. There we go. Putting holes in the brand new machine. There she is, not too bad. Not that it matters, but I can tell you that the casting on the foot is definitely thicker on my other lathe. Now we start cutting and drilling. Beautiful, hacking up brand new machines. you can kind of get the idea here. All right, and we'll grind that up so it's not a rubbing hazard, but don't worry, it's not gonna rub. We'll tighten that screw up and we'll make an end cap here, like a little 90-degree deal. So that way this is covered. All right, let's see if I can show you what we're doing here on the back. It's kind of tight to film, but here's the concept. So we have this pipe that I welded a 90 to another pipe. The wires are gonna come out of here. We'll 3D print a cap, but this will allow us to bend the wires and everything around that 90. Then we have a piece of stainless here that I just had, and that's gonna go the whole length, and that's kind of like the cable tray. It's super overkill. This is probably like a $300 piece of stainless, but I had it on the shelf. I've had it for many years and wasn't using it. I'm just using stuff that I have so far. So you can kind of see what we're doing here. Pretty straightforward stuff, nothing too crazy. The wires will be in the back. They'll be behind these existing trays, and since we're using or making a new tray, we can accommodate it so it doesn't hit this, but it's a good way to redirect the wires out of the front and out of the way. The front is pretty much done and it turned out pretty good. We went ahead and reused this cap that was on the top. We just did a miter cut and returned it back, welded it together, and you know, it just keeps everything nice and clean and sealed off. We have a nice big hole in the back so we can pass our coolant line through. I want to pass the coolant line through here and into this cable tray and up and back to the spout, so that way we don't have any problems with snagging. Luckily this cable tray has tons of room in it, so that shouldn't be an issue. And as you can see, now we can stand close to the machine and our shins aren't hitting that cable tray, and we have tons of room here unimpeded to fabricate our custom coolant tank chip tray, and we can do that at any point without downing the machine, which is really, really nice. Now obviously it'd be nice to have 2 of these, but for now we probably are going to use the front chip tray like 80% and the back one 20%, or maybe even 90-10. So I think this is a good compromise for now, because this will allow us to kind of fix the major issue. And if I only have to empty that second chip tray out occasionally, you know, once every couple months, I think I can live with that. But the main tray we're filling up with day in and day out is nice and accessible. So I'm really, really happy about that. Let me bring you around to the back. The back is pretty much done. We just have to clean up some of the wiring in the panel. And this turned out pretty dang nice for using only material that I had on the shelf and trying to do this very quick. We're only in like 3.5 hours today, which is quite impressive. I thought this would have taken a lot longer, but we ended up creating this pipe here. We actually, this hole in the back worked out really well because it allows us to fish around this bend. So I'm gonna 3D print a cap to take in and out of there when we need to do any more fishing. We used this stainless tube. That tube I actually had on the shelf, and it worked out really, really nice. This is nice and oversized, so we have plenty of room. So when we route our coolant hose throughout there or anything else, there's tons of room, which is really, really nice. And it is modular. So if we need to take this off, we just undo that screw and pull it off. And overall, I think that turned out really, really nice. And being stainless, you know, if it gets wet or anything like that, it's not gonna rust, which is great. We then transitioned it into some of this flex conduit, which is galvanized, and we just quickly welded the galvanized onto that because I didn't have any junction, and it's on the back of the machine. So that worked out fine. We have the wires pass through there, and again, galvanized. Shouldn't be an issue with rust, not like I'm too worried about it back here, but the wires are nice and clean. I am very thankful to Lion for providing extra wiring because we did not have to extend any wires. Here's a look inside the panel, and I think this is actually going to work out really nice. We do need to hook up all these wires, but since they did such a good job with the labels, shouldn't take us too long. And now instead of running everything through the one, we have 2 separate runs, so that'll give us a little bit more versatility. I know we have a spare wire in here because I eliminated the light, so we will use that to power our lube pump. and I want to run the lube line all the way through the cable tray to the back and through here, and then we'll put the lube pump externally. But unlike on the pacemaker, we'll have the lube pump right on the back here so we can fill it up, but it will be serviced over at the cross slide, so everything will be really clean and really nice. So the last step is just to get these wires cleaned up a little bit and reinstalled, and we should be good to go in terms of the wire modifications. It is about 10 p.m. in the evening, and I got in here around 10 a.m. this morning, and we started using this machine. Now, I use the machine probably 80% of that time. The other time I spent eating lunch, eating dinner, answering emails. But aside from that, in one basic day of doing work on the machine, we have filled the chip area that is concerning to me. So first and foremost, the base is probably like 70% full, or the tray. And more importantly, this front cavity is like 90% full, and this second cavity is like 80% full. And throughout the day, I did clean these out and tried to get them to drain as best as possible. But I think this just highlights the poor design of this chip tray. In one work day, you basically max out this tray. Even like we talked about before on my pacemaker lathe, I have the floor, which isn't a tray at all, and I can get easily a week out of that before I have to address it. So the fact that this machine is worse than that machine with nothing, I think is a problem, and I think we're gonna be able to improve upon that with the new tray. But I wanted to just show you in real time after a full day of usage. That way you can see it and not just hear me talk about it, on how this gets filled up and how inefficient it is. So hopefully when we do our design with our wider tray, we can compare the results and see how many days of work we can get done without having to pull out the trays. The other thing that's worth noting is we do not have the guard on here, which we've talked about before, but I am running this temporary kind of coolant shield that kind of swivels. I take it on, take it off when I need it, and that is doing a good job. However, I noticed that a lot of coolant builds up here and runs down the front of the apron. It doesn't matter where this shield is, it's just kind of the way it's designed. That's totally fine, but when we design our chip tray, I want to see if I can kind of kick up the tray in the front just a little bit and actually kind of mitigate some of the coolant that drips off of this so it can be caught and recycled, because this 3 to 4 inch gap in the front where the chip tray kind of falls short actually makes a big difference, because a lot of coolant runs kind of in a line here where this apron is. We got everything wired back up and everything turned out really nice. Obviously it's not quite as clean as the factory, but clean enough that we can see what's going on. And there's a pretty good chance I'm gonna need to come in here again and unplug some of these, so I'm not gonna overly get concerned with it being perfect. Next step is to move around to the front so we can start on fabbing up our coolant tray / pan. We got all the room in the world to work, and I went ahead and picked up some sheet metal and some box tubing. So now we're gonna go and design up a new chip tray coolant pan and start working on getting that fabricated. Kind of what I figured. All right, let's use the proper tool. Take two. for the material for this project, we're going to be using steel. Now for the other Lion lathe, I promise we are going to use stainless steel like I promised and go all out and do a huge flex because I love that machine. But for this machine, we're here to do work and make money. And steel for coolant tanks works. It's not going to last for 100 years, but it'll last for 20 years. And especially if we use the right coolant mix, it should be fine. And steel is a lot cheaper. So we have 4 sheets of 1/8 inch 4x8, which I know is definitely overkill. But I wanted to get thicker material here, specifically for the front and back. Because I know that we're going to be bumping up against this, and I don't want one of those long strips of sheet metal that's floppy, right? We want to make sure that this is going to last, and in 20 years it's still in good shape. So it's going to be a little bit more weight, a little bit more money, but it should be sufficiently rigid. Now ideally, when you're making something like this, you would get this stuff bent in a break, and they will do it for me. But not on a timeline. They need a week or two, and I had a day or two of opening and jobs, and I need to knock this out now. So unfortunately, we're going to be cutting and doing long rip welds, which I hate, but you know, it's because we're working on a timeline, and that it just is what it is. We also got some 14 gauge as well. That's a little lighter duty. I don't know where I'm going to use that, but I don't need to use 1/8 inch everywhere. It's a little overkill. So we're going to kind of bounce back and forth and figure out where we need strength. We'll use this, and where it doesn't matter as much, we'll use the 14 gauge. This stuff I think was pretty cheap. I only paid like $110 per sheet, which I think is kind of cheap for this. Maybe it's not. I also picked up some 1x square tubing just as some structure. I don't think we're going to make it the full flat bottom on this without this sagging. So if we need to build a small frame, we have that just for more rigidity. The name of the game for this thing is durable, right? We want this thing to be able to hold 600 pounds of chips and 200, 300 pounds of coolant and not be bowing and flexing. So it's going to be overbuilt, it's going to be sweet, and that's just how we're going to do it. In terms of the design, this is all freeform. No CAD drawings, no hand drawings. I'm doing this as I go. I'm going up to the machine, I'm taking measurements, I'm making guesses, and I'm doing some corrections. We're doing it that way because I'm on a little bit of a timeline, and you know, this is relatively simple. And I don't have the idea fully fleshed out, and this is a good project to build a little bit, stop, think, make adjustments, make tweaks, and the risk is minimally low of us screwing this up. So that's why we're going to take that approach. So the first step is to go ahead and figure out what the front angle is and length, and we'll cut a rip of that, then we'll cut the bottom, then we'll cut the back. We'll have a nice little U, we'll make the end caps, and then from there we'll work on the bracing in the center, the cutouts for the casters, and then make the dividers we need and the tray to isolate the coolant area from the chip tray. The first piece we're going to cut out is going to be 17 tall, 66 inches long. This is going to be the first angled piece on the front of the tub of the coolant tank. We got a few pieces up on the bench, and you can kind of see the idea come together. The front is going to be angled. I think it looks nicer. If you look on a lot of the older chip trays on Monarchs, LeBlancs, they're angled as well. The other benefit for us is because this top rail is going to contact our shins when we're standing at the lathe, by angling it, this allows a little bit additional clearance for our boots at the bottom, so that way we don't have to kind of step back 4 or 5 inches. So that'll be really nice. We're going to have to reinforce this area here because this is going to be a really large area for the coolant to fill up. And then we're going to have a tray that's probably midway that's removable, and that tray is what the chips will sit on top of. So that's going to be really nice because that's going to give us a nice rigid frame so the weight of the chips are not going to bow. And then if we need to access and clean the coolant, we can remove that removable tray and we'll have a 100% access from the top. So it'll make this coolant sump, if you will, really easy to clean out and service. So that's kind of the game plan. I'm gonna get some of this stuff tacked up. I cut the top a little bit crooked by like a quarter, so I gotta clean that up. And then really, once we get it tacked up, we'll get some cardboard up here for the ends, and we'll start working on the end caps. Let's talk mobility. I want to be able to move this in and out very easily. And when you look at a lot of coolant pans or chip trays, some of them don't have any wheels. Some of them are just friction, you know, pulling it out of the lathe tray. On the CNC, they do use casters. That's a more common design, but they have a small 2 or 3 inch caster with a bracket kind of extending out. And the reason they do that is they don't want to put a 3 inch caster underneath because it raises this big, heavy tank up off the ground. Now we're going to try to combine the best of those ideas. I want to use a large diameter wheel. The reason for that is the bigger wheel you use, the easier it is to roll around. But the problem with a large diameter wheel is if we stick it underneath, it's going to bring our tank way up off the ground. So what we've done is we've cut 4 holes. We're going to take and we're going to install these wheels in these holes, and we're going to build a box around the wheel. That's going to allow us to have a large diameter wheel, but keep this low to the ground, and there should be really no con aside from the additional work of making 4 boxes and getting them welded and watertight. Once we get those boxes installed, we're going to put some bracing so that this is sturdy and the load is distributed among the area where the wheels are at. But that should keep the wheels concealed inside the box of the actual coolant tray and minimize chips and debris getting into them. And in that same theme, we've chosen a metal wheel. I like the poly wheels, but the metal wheels keep the chips from getting embedded into the plastic. And so that's really what we want, since there are going to be chips probably laying on the floor underneath this. So with that being said, we need to build these square boxes, and in order to save time, we're actually going to start out with some square tube that's already close to size. So I have a large piece up on the rack. We're going to get out the forklift, get it down, get it cut up, and then all we have to do is cap off the ends and then go ahead and weld those to the bottom. We got these cut out, and this is kind of what we're going for. I went ahead and I had to modify these casters. You've seen in the last shot that there was like 1.5 inches between the caster and the top plate. And I thought about it, and I just figured it was easier to chop these down. Otherwise, I would have had a big gap at the bottom. And so what we did is we went ahead and drilled and tapped 4 holes here. So that way we can mount the caster, and you kind of see the concept. Caster is going to sit inside this tub. This tub will be flipped over and mounted. And currently, right now, there's a gap here of about 1/2 to 3/4 of an inch. So when we lift this up or push this down and weld this, that's going to mean that our caster is captured, and it will put this off the ground about 1/2 to 3/4 of an inch. And the only thing we really need to do is to cap both ends and then get these fully welded to this plate. And this should work out really, really nice. I thought about doing a bunch of crazy stuff to make sure that we don't get any leaks from these holes. But at the end of the day, we're going to use some shorter screws. We're going to use some thread lock. And then once everything is done on the inside, we'll go ahead and just silicone around them It's going to save us some time, and I think this keeps everything mounted nice and low profile with minimal stick out, which is what we want. So that's kind of the game plan there. So I'll go ahead and get the caps on here, get it welded out. We're not going to do any full welding on this until everything is sort of tacked and positioned. But once we get these capped and tacked, we'll move on to the next step. We got our wheel caps tacked in place, and I went ahead and added a center stringer and tied everything together and just tacked it in place. We also do have a hole here, not sure how easy that is to see, so we're not impeding our coolant flow. But the next step is to consider coolant flow and how we want the coolant to be routed. Now, we could be fine just with a giant empty tank. It's what they did on the Lion previous. It's what they do on a lot of smaller machine tools. But on the lot of larger CNCs and more thought about equipment, they use making a large coolant tank as an opportunity to sort of filter the coolant. They use weirs and or baffles to direct the coolant in a certain path and sort of filter out sediment, trap oil, and any sort of debris or chips. So in this case, we want our coolant pump to live here. And what we're going to do is build a little section for it that is divided off from the rest of the tank. And then we're going to have a couple different weirs or dividers. And then we're going to kind of design how we want the coolant to flow. I'm kind of doing it as we go, but I know I want the coolant over here in the back corner because that's going to be near the center support of the lathe, and that's going to work out nicer because it's going to make a shorter hose run because we're going to be running our hose into that center knee portion. And other than that, everything else is just going to be for coolant. The inlet is going to be something in the center, something large and long as opposed to like two little things like it currently is. And then from there, the coolant's going to flow down, and I have to plan out how I want it to get to this back corner. But I want to kind of be strategic in how I do that so it can help prolong pump life. Otherwise, if you didn't do anything like that, pump life would probably be fine. But planning it out does help mitigate junk getting sucked up into the coolant. And there's going to be multiple stages of that. We're going to be running a filter on the coolant housing. We're going to be running a filter on the intake. We're going to have the weirs, the baffles. And the goal is, if we design this right, you know, the coolant motor should always have clean coolant and should, you know, pretty much last forever. So with that being said, I'm going to kind of do some thinking and brainstorming, and then we'll use the thinner plate to make some of these baffles and figure out where I'm going to lay everything out. As usual, things are getting out of hand over here at Vanover Machine and Repair, and this thing is turning into a full-blown project. But this coolant tank is going to be very, very trick, and I think it's going to work extremely well. So let me explain what's going on here, because we got a lot. So the idea here is we're trying to increase flow and we're trying to increase filtration. So typically a coolant tank like on this machine is just a box. And the problem with that is that coolant can come in and come right over to the coolant pump with very minimal circulation. And there's problems with that, mustiness, sometimes the sediment that's floating on the top doesn't really get mixed around. So we're trying to kind of do one better and to get the coolant moving to decrease smell and help with filtration. So in this case, our coolant dump is going to be in the center on the other side of this divider, and the coolant is going to have a notch in this divider that we haven't installed. So the coolant has to come out over here, and it has to travel all the way around back to the actual pump. That'll give us really nice flow and keep everything moving, and also help with making sure the coolant gets mixed properly. I know the right thing to do would be to mix the coolant and the water first and add it to the tank. But the reality is me and like a lot of other shops, they pour water in the tank, they add the coolant, and then as the tank runs dry, they'll add some coolant, they'll add some water. They kind of do it, you know, by feel. So having good flow in a tank like this helps, because sometimes when you do it the way I do it, you'll add water and then you'll add fluid. It takes a while for that to get mixed up, and this will kind of help with that mixing process. So just to give you an idea of the path, So when it comes in through here, we're gonna have on top of this tank some filtration paper and a grit material kind of similar to what's over here. So that should eliminate all of the chips and some of the oils from even entering in the tank, but there will be some that make it past. So once it comes in the center section, there's gonna be a filter here, and then it's gonna exit, being filtered once. It'll have to flow all the way over here, and it can start to enter the back chamber. Once the fluid comes through here, it has to make it through a large perforated sheet, and that will catch any chips that didn't make it through any of the other filtration systems. Once through there, it has to jump through this small little hallway, and there's a nice trap here to collect any debris that makes it through here, and then it has to make a direction change and kind of come around from there to here, and that'll allow some sediment to collect in this corner and that corner, and then it has to make it up a small little ramp, and then lastly through a very fine filter mesh where it can come in the last section to the coolant pump. Now obviously when this is going to be fully filled, you might be thinking, well yeah, this is all going to be covered, so how is any of this stuff low going to make a difference? And that's a good thought, but the reality is some of this stuff is going to settle, and even if the level is high, that settled stuff will kind of get caught on some of these lower features and kind of help promote filtration and minimize stuff that gets sucked up from the coolant pump. So once all that's said and done, anything that comes out of here should be fairly clean and fairly circulated and mixed, and then it will go over to the machine. So the next step is to get this center divider in and create our cutout, and then finally get the back and front and kind of continue on with the process. I've just been kind of enjoying my time off, building and you know, kind of doing some engineering here and learning as I go. So I'll go ahead and continue to do that, and then I'll bring you back once we made some more progress. It's been about 4 days of solid work, and we got this pretty much finished out, minus the paint and the sealing. And I want to just give a quick rundown on how this finished out and how it compares to the old chip pan / tray. So off camera, you can kind of see the old tray here sitting next to it. I'm going to slide it over just a little bit so you can see the difference. Two main things. Number one, this tray is 2.5 inches deep at its widest point, and that point is a very thin crease in the middle. This tank is about 9 inches deep, so quite a bit of a difference there. This tray sits about 5 inches from the bottom of the casting. This tray sits about 9 inches from the bottom of the casting. So between an increase in depth between the actual deepness and this being farther away from the casting, this is just going to hold way more chips, which is going to be really, really nice. The other major difference is this tray had a major problem with drainage. Now you can see that this tray is sort of pitched in this way, however, it's not pitched side to side, and the drain is on one side. So it was very, very common for chips to pile up right here by the drain. And this drain is on the headstock side, which is a bad design because a bunch of chips would pile up here, not so much over there, and then all the coolant would sort of pool in the center and it would stay there. It would get stuck because there's no sort of side-to-side pitching. This design over here is similar in that it only pitches in two real directions, but the drain is much larger and it's offset from where a majority of the chips are going to be collecting. So the majority of the chips still are going to be collecting over here, but there's a large portion of the drain and it's much larger, so drain back should be much less of a concern. The other thing that you'll notice is that this design is much more severely pitched, so any coolant that does run into this is going to be moving at a much faster rate back to the drain and should spend much less time sitting in the tray. This area over here on this side is actually pitched as well, so everything in this region here is fairly pitched back to the drain. There's really only a small strip that isn't pitched, and that is these two sections here. So there will be some stagnant coolant there, and then if anything gets into this area over here, obviously it's just going to pile up. But I think this is fairly well sectioned off, and 80% of the coolant and chips is going to collect in this area anyway. So I think that's not going to be an issue. So in regards to this area over here, this is where the coolant pump is going to live. So I went ahead and kind of sectioned this off so that most of the coolant is going to be avoidant of this area, but the coolant pump lives in this area, and we'll remove all these dividers here just to kind of show you how things ended up underneath. But all these dividers and caps are bolted down for easy access. I wanted to make sure when everything is down, it's nice and tight and there are no leaks and all the chips are going in the direction that we want. But down the line, when we want to service this and get in here, we can easily remove all of this stuff, and we're just using standard 1/4-20 bolts, so we'll be able to take these in and out for many years to come and not have to worry about sealant or self-tapping screws or anything like that. One also thing that I'll mention is our filter paper did come in. So this paper or fabric can be cut to length. And because we have a nice little indent here, what we're going to do is we're going to cut a bunch of these and we'll lay one in the bottom. And this will do a really good job preventing finer material from entering into this grit. So as an example, we just ran a job where we did a bunch of cast iron. That went right through the filter and almost nuked our pump. But in this case, this filter paper sitting down here in the bottom would prevent the cast iron from making it through that filter and prolong the life of our pump. And every time this gets cleaned out, we'll just replace this. This stuff is cheap and easy to replace. Let's remove some of these covers and just kind of show you what's going on underneath and how we finished out. So this front cover, pretty straightforward here. This is the largest area, and the coolant is designed to come in through this grate. It's forced through this area here. And this cover that I just removed is an access cover, so we can take out another filter, which is just a 3M Scotch-Brite pad. So the coolant will come in through here. It has a really nice big volume to fill, which is good in comparison to our other one. It will mitigate clogging and it will mitigate drain back. The whole coolant comes in through this huge area. It's going to be forced through this filter here, and it's going to have two paths. One path where it can kind of curl around to the back, which is a dead end, doesn't go anywhere. And then another path where it's going to be more likely to come is down this hallway here. And the reason it's going to want to come this way is the coolant pump is sucking from the back, and it's kind of bringing a current of fluid this way, or liquid. And so it'll come down this hallway. There's a little kind of switch back here where some sediment can collect and then go around to the back. And we already kind of talked about those chambers, so I'm not going to get into that. But I'll remove those plates so you can see how it finished out, and then we'll talk about finishing. This is kind of how we finished out in terms of baffling. Everything was pretty similar on this back half in the last shot, but you can kind of see coolant is going to escape from here and make its way all the way around to the back. And this is really, really nice. It creates good coolant flow, and also our coolant pump being here instead of right over there where all the chips collect, I think is going to be a much better improvement. Now in terms of welding this, so this is fully welded out. but you got to be careful when you're welding sheet metal. And we did have one mistake that you could probably see. This area is fairly bowed back here, and I'm going to roll with it instead of fix it. And the reason for that is you want to make sure that we fully weld this as best we can, so that way it doesn't separate from the frame, meaning all these braces. But you have to be strategic about it. Yes, you can go around and tack everything and you're not going to have problems like this. But what I found is if it's only tacked, when this shifts and twists, the tacks are going to pop. So it's all about being strategic when you're welding. And ideally, we'd get everything in and tacked first and then come back and fully weld that. But some of this stuff I needed to be fully welded first. So I got most of the center section done, tacked, and then we fully welded sort of the center bracing. But later I came back and added these kind of supports for the shelves. And I only did that because I was planning as I went. But that meant that I was fighting some of the welding like this that I did earlier in the stage. So that's just something to be aware of when you're building something like this. But overall, I think it turned out pretty good. The actual main tub is welded twice. So it's welded with fillets on the ups going all the way down, and then on the bottoms, it is stitch welded on the inside, and then everything on the main tub is fully welded on the exterior. So these front joints are ground for visualization, but all of these bottom welds here and on the back, I left it unground for strength and for, you know, not removing any more material. So we shouldn't have any problems with leaks, but we are going to be using a sealant just to kind of double check ourselves. So in terms of sealing this, we're going to be going with a 3M 5200 marine adhesive sealant. And what we're going to do is we're just going to come clean all this with acetone and come in here and basically caulk everything up. That sealant is really good for adhering to metal and being submerged. So that'll make sure that if we missed anything or there's any pinholes in the welds, that covers that. Now once it's done, we're going to go ahead and prime everything with this carbit and then paint it with this carbit paint. I'm sure there is a specific paint for coolant tanks, but I wanted to get something that I could get readily available. And I've used this paint on gates and fences, and it's designed to basically be like a paint on powder coat. It's designed for gates, fences, art pieces, anything outside that's exposed to sun and water. So it's an enamel. It goes on very thick and it's very durable. Has a little bit of a longer dry time and it's a bit gummy to work with. But once it's hardened, I think it's going to be really nice and really durable, and I think it'll work well for keeping everything sealed and looking nice. So next step is to go ahead and get everything sealed up, and then once everything is sealed up, I'll go ahead and get this primed and painted. All right, guys, we have Daniel here in the shop, and we're going to be looking at the Lion lathe. In the last couple shots, we were able to disassemble the machine, and I saw some scoring, and I wanted to get Daniel's opinion and or help kind of before I continue. Obviously, we're not rebuilding this machine. We just took it apart to look at some of the oiling, but I want to get your thoughts and feedback. So now that you've looked at the top slide and the apron / saddle, like what are your initial thoughts on the way this is designed, put together, the condition, the quality?
Yeah, so I think my initial impression is I'm a little bit surprised that there's some slight scoring already on the top of the saddle here. You can feel it on both sides. There's lines that go the entire length of it. I'm not sure if you'll be able to see it on camera. You could just barely pick it up with your fingernail. And that's not such a big issue. Functionally, we're gonna stone it out so that that's not there anymore, but you know, that's actually starting to pit over on this side too. So you shouldn't have that after a couple months of use. That's really like, this is very premature wear. And so the question is like, why and how? That's what's going on in my mind. And it could be alignment issues. It could be there's unnecessary clearance in here. Maybe the top side isn't properly matched. So there's actually like air gaps where material or where chips are getting inside. That's a possibility. Could just be Kyle's not lubricating his machine properly, which I highly doubt. But something else that I'm noticing just by feel is that the surface finish on the dovetails is not that great. You can feel, even without looking at it, you can feel that there's chatter marks because this was ground. That doesn't mean it's bad, but I think surface finish wise, it should feel very smooth. Like this looks good and this feels good. This is obviously just clearance up here.
Nice work on the clearance, guys, where it counts, you know?
Right, I want to be like apprehensive to point fingers and be like, this is not good, because we don't know yet. It could be very, very close. But as Kyle is saying, the clearance on the top of the saddle looks great. Maybe less so on the more critical master side. Maybe it was a Friday afternoon, 4 o'clock, they're trying to get this thing out the door, who knows. But what we're gonna do right now is gonna put an indicator on the flats and see if they're coplanar, just to get an idea of where that's at. And we're also gonna put an indicator on the doves to see how parallel they are. Because Kyle and I were talking earlier about the game plan, and I'm thinking, you know, while it's apart, we might as well put some blue on this and blue up the bottom of the top slide. But in order to do that, I want to make sure that this is looking pretty good as a master, if this is what we're going off of. So what I'd like to do is make sure this is within, you know, maybe a 0.5, 6 or 7 tenths flat and parallel. And then we'll put some blue on it and blue up the top side and see what's going on. See if they're really matched together or not.
I like when you stone stuff, you can sort of see the high spots.
Yeah, you can see how bad it is.
Yeah.
So there's a ridge here that goes all the way across. And there's a ridge here and a ridge here. So there's 3 high points. And this looks real low on the outside. This looks low in the middle here. There's a big scallop in here. Not that that really matters, because that's all covered anyway. But inside, they machine out clearance. That's usual. You know, you cut out that corner so that you don't have any interference. So you have the dovetail and the flat, but right in there, when they were grinding, something happened. They took too much material out, and there's a big scallop right in there. Again, not
critical,
not
but
gonna affect anything other than just it sucks. Looks like there's some, I don't know if this was really scraped at all. It looks like there's some lines that I'm not sure is from wear or if it's from grinding. Doesn't really feel that good. Not very smooth. But we're gonna stone it a little bit. Let's see if we can take a measurement. This is an interrapid half-thou indicator. So you can see how much that needle is jumping around.
oh dear Lord. Okay, feeling a little better. It was like a thou.
Maybe a 0.5 overall.
Yeah, but that could be undulation. So.
Right, it's hard to tell with the surface finish. Maybe a little
maybe
bit
up
minus,
to 1 thou, maybe?
a little bit minus in the middle. So, not bad. 0.5 probably overall, as far as parallel for the dove. We'll check the flat also, just because I'm curious. 1,000, 1.5-ish. About 1,500 flat over the flats, and then about 0.5 parallel. Personally, that tells us like it should be better. For sure, it should be better.
Right.
But I don't know what sorts of standards new machines are coming out with. Like I don't know what the factory says is good or not good. I can tell you that the surface finish is not good. It's within 0.5 parallel, which is good. I think there are some issues with it, but it's probably good enough to be able to use as a master to blue up the top side, which I think we'll probably just go ahead and do anyway. So you can feel these,
The glinting or whatever.
this oil groove is razor sharp. The edges of that should have been deburred for sure. You can see all the high points on here. You can see actually the original grind. You can see some of the chatter from the original grind. Right, maybe it was running a little hot. Looks like they cut the ends a little more than the middle. Because this thing was grinding like that. You know, it was kind of bananaed after it came off the grinder, so they cut the ends. Which, you know, it's whatever, it happens. But the little bit of, I wouldn't say a score, but you can see some wear lines on this side. That's a score. I mean, not terrible. I think scraping looks kind of funky to me, but.
I think the biggest takeaway that I had was like there was a lot of sharp edges, and there was definitely a lot more lines than I would like. You know, you can call it wear, you can call it whatever you want, but you know, at a 2-month-old machine, you definitely shouldn't have that many lines vertically in the machine, you know, and that can only happen from traversing it back and forth.
Sorry, I'm getting all this blue pigment all over your nice
Smurfing me up, man.
White saddle.
So I wanted to do this like week 1, and Daniel was like, listen, man, like, you know, you should use the machine. Like, don't be an idiot. Like, it's probably fine, you know. So what did we do? We made it like 2 months. You know, I did use the machine. We did make some money, you know, but at the end of the day,
and then out of the blue, I just get text from Kyle that no explanation, just saddles torn apart. It's like, okay, what are we doing? Are we scraping this now? What's going on?
Yeah. But hey, I'm glad I did. I mean, I am glad I waited a little bit just to, you know, confirm, yes, these things do bother me and I want to fix these things.
Uh-oh. Hear that?
I tried not to hear that, Daniel.
Tight up in the front. A little loose in the back. All right, so we just did our acoustical analysis, and it sounds like it's tighter in the front and looser in the back.
Okay, what are we seeing, half thou there?
And so on the front, just to take a real measurement, we're about there's a half a thousandth play on the front. So what we're doing right now is checking the shake. I want to know if the clearance on the front of the gib is the same clearance on the back of the gib.
Right.
So that'll tell us if the gib is tight up here and loose back here.
The taper is not accurate.
The taper is not right. And we'll be able to tell exactly how off that taper is by what that indicator is saying. And the reason that's important is because if your taper is tight in the front, then you're going to get more wear on the front of whatever is moving back and forth. Mm-hmm. In this case, it'll wear more on the front end than it will on the back end. So we're going to put the indicator on the back and see what that looks like. And you're seeing more movement because it's kind of rebounding. It could be because we don't have the gib screws in there, so it's shifting a little bit, but it's repeating. So we're calling that a half thousandths play.
Oof.
All right, so we'll set that on 0.
Yep.
2,000. It's about 2 thousandths. So half thousand on the front, 2 thousandths in the back. Tapers out 1.5 thou, which is not good. If the taper was out a half a thousand, 6 or 7 tenths, that would be permissible, I think. But ideally, you want them to be straight so that you have even wear across the whole thing, and the flats and the dovetails wear evenly across this whole part. Because right now, you're just gonna get a bunch of wear on the front.
We can't have that.
We can't have that. I'll put some red lead on the gib and we'll slam it in and see what the bearing looks like, because now we know that the front is tight and we'll see what the bearing shows. But we also know that we have about 1,000, what did we say, 1,500, maybe total indicator run out between the flats and the dovetails.
Sure.
Dovetails being out 1,500 over the length of it, and the flats being out
1.5 thou.
1.5.
But it isn't like plus or minus 5 or 10 thou.
No,
But also, you know,
a
it
couple
isn't.
thousands on a brand new machine is, that's out of, as far as what I would understand the specs to be, that would be out of spec.
Right.
Everything that gets rebuilt is within 0.2. So those are the standards that I abide by, and I understand that it's not economical to manufacture equipment with that type of standard, especially a big lathe. I think for a grinder, yeah, I think it would be closer for sure on a new machine. OD, ID grinders, surface grinders, yeah, it'll be within 1,500. I think it probably needs to be as a new machine, otherwise you couldn't make good parts on it.
Right.
But a couple thousand on a big lathe, can you still do the work you need to do on it as is? I'm sure you could.
Yep.
I'm sure you'd like it to be better. So this is highlighter, also known as red lead. It's used as a base for taking out the glare on when you're bluing stuff up. So typically, like if you're scraping something that's really hard to see, you can put red lead on it as a base and wipe it off with a rag so that it's super thin, and then you blue it up like how you normally would. In this case, for checking gibs, it's easier to see. It's not as accurate of a test, but it's easier to see on gibs where the bearing is to get an idea. Like, we know it's tight in the front, so this stuff will come off on the front when we slam it in. And if it doesn't, then we know something else is going on. Maybe the nut or the clamp is tight or something's weird going on. But it's just easier and quicker than bluing up, because we'd have to pull that top side off every time we'd want to blue it up, which is annoying. So it's easier to put this stuff on and it'll just come off when you slam it in. So I'm going to put pressure on the gib and push it to get a rub on it. Then I'll come back and slam it in. So on the rub that we took when we pushed it forward, looks like there's halfway decent bearing across the front. Again, this is not a bearing test to see how flat this surface is. This is just a gauge to see how our taper's looking, and you can see on the back of the gib, all that red lead is gone on the front, so we know it's tight up here, and there's almost nothing gone back here. So we know that for sure, because we did 3 different tests, and it's a bit redundant.
Right.
But I think it's helpful to get an idea visually of what's going on. We know that the gib was scraped in to the front, but the taper wasn't right. So that's kind of disheartening. So taper's out almost 2,000ths. The more you know, knowledge is power. Kyle is probably just going to use it as is or make some changes, I'm not sure. But I think while he had this apart looking at the oil, we might as well be hypercritical of things and just kind of see where they're at. So now we know where this is alignment-wise. We should check square. I'd be curious to see how square this master is to the bed. I know Kyle was taking some big facing cuts, and I think they turned out pretty good, so I wouldn't be too alarmed. But for now, what do you want to do about it? Is this going to fly? Is this not going to fly? I'm certain. Let me say also, I'm not in the business of pointing blame or saying that this should be better or shouldn't be. You know, it is what it is. It's a lathe. It's within a couple thousandths. He can make good parts on it. So if you can make good parts on it, then it works. Personally, my belief system is it should be tighter. But I'm not manufacturing lathes, so I don't know how much that costs and what their profit margins are and what goes into all that stuff. So I'm in the business of fixing things and rebuilding machines. So my tolerances are different than manufacturers. But it's maybe just nice to get another rubric to go off of when you're looking at a piece of equipment like this. So what do you think, Kyle?
I think we're gonna fix it.
You're gonna scrape it in? Ooh! I'm gonna scrape it in.
Oh man. We knew it was gonna happen.
Yeah. Kyle and I are just exchanging looks.
Oh man.
I mean, you know, there's contact. There's some blue on there. Oh, there's a number of ways you can look at it. At least it's touching here, it's touching in the middle, and it's touching down here. It's also touching out here on the end. It's touching on this strip for sure. I was a little bit liberal with my blue also, you know.
Yeah, which helps this.
I laid it on a little bit thicker to get a better contrast. So this is maybe an embellished understanding of what this surface relationship is looking like.
Meaning it would be worse.
Meaning
if we properly blued it.
If we were bluing it the way that you would when you're scraping, it wouldn't look this good. And you can kind of tell that by these lines that are coming out of, like, there's a high point right there, and then you can see these lines of the actual blue that's like smeared. When you see smearing like that, you know the blue's too thick, and it's really dark also. So there's also some coolant that came through on this side, which is messing us up a little bit. Not going to cause us any issues because we know what's going on here, which is not a whole lot, unfortunately. But you know, it's making contact all the way across, which is better than not. You know, this is a small part too, so maybe they scraped it in and it distorted. You know, it shipped from overseas, so it came a long way, apparently. So bearing's not good. You know, my consensus is the bearing's not good.
Yeah.
I'm also surprised that they didn't use turkite on this. I thought that was sort of a weird decision.
And why do you feel like that's a weird decision?
Well, if you're manufacturing a piece of equipment, this is more time intensive to scrape, and you know, cast iron on cast iron takes longer to scrape and machine than turkite. And also you can just rip turkite off and relaminate it, as opposed to regrinding and then rescraping. And it's smoother too, you know, as an operator, it's smoother to use turkite on cast iron. And especially, you know, tops of saddles aren't usually scraped in, those are usually ground, and the bottoms of top slides are usually turkited and scraped to match. So if you can get the saddle really good as far as the grind quality, then the turkite on it, it just feels like butter. And you can feel the resistance on your pacemaker too, that difference between this and that.
Yeah, now we gotta think.
Right.
Because this isn't something where it's like, oh yeah, you know, I have the warm fuzzies, let's slap it back together and it's fine. This is something where it's decision-making time.
Right. Yeah, and I think it begs the question of, like, what do you expect something like this to be? I would expect it to be better, but I don't make machines, like I said, so I would like to see something a little better. Brand new, couple months old, a little bit of scoring already. Also, like, just these oil grooves are not really great. They're razor sharp. This edge is super sharp. This should have been deburred, definitely. And because the edge of this oil groove will start to wear because it's so sharp. It should also have been machined differently. Like this is a straight groove all the way down the length of it. They should have done something with, like, going across the length of this. Or even instead of doing a line that goes all the way down the middle, they should have done like a diagonal.
Angled, yep.
Right, a diagonal that goes like across.
Because the problem with this is you'll have a high spot worn in the lathe here because that line just traverses and you always have a section that's skipped basically.
Yep.
Right, now technically this little flat here would run over that, but even still, you know, that's kind of what they do here with the scallops. It's kind of like maybe a ghetto way to do it. It kind of looks like the scallops are cast in maybe. You know, as opposed to the T's, similar concept. Obviously, I think it's clear that they try more than maybe the Chinese manufacturers, but you know, obviously whoever engineered this isn't a machinery rebuilder, because this stuff is just like, you know, machinery rebuilders and people who manufactured equipment back in the day, you know, they would kind of know better.
Right, different considerations.
Yeah.
And little decisions like this make a huge impact of what happens to the top of your saddle.
Right, long term.
Long term, whatever that's worth, you know, it's all the little things that add up to making a really nice machine. But you know, they got the general idea of the scraping on it.
Yeah, it is scraped. There's stuff that isn't scraped at all.
Right, and maybe we can see the master.
Oof.
The master has
It's got contact, I don't know.
There's definitely a deep score in it. I could have maybe added a little more blue. Definitely high right on this corner here, and high on the back. But you know, they also probably relieved the middle a little bit. Yeah, what you're supposed to do, you're supposed to cut the middle out, but looks like there's just not really any bearing. You can see definitely high points over here and high points on the front. And you know, the good 60–70% of this is not touching. And also that poses an issue because of how much this top slide hangs off the back. So the more you traverse forward making a cut, the more this hangs off the back, so the less this bearing is touching, and then you start to introduce bearing here. As opposed to
loose, yeah.
Right, so if this was straight, it shouldn't matter how far off the back
right,
of the
you have
saddle
good contact the whole
because
way.
you know it's flat and you know it's making good contact, exactly. So in this scenario, we don't know what the bearing is like when you're realistically making a cut on it. Sort of the same story, I think, with everything else we've checked so far, which is not the worst thing in the world, but also not the best. For a new machine, I would expect something a little better.
It's been a couple months and we finally got this tank completed. Now, I didn't show painting it. It's pretty easy, guys. We did bed liner on the inside. I went ahead and caulked the seams prior with seam sealer and 3M 5200. Completely unnecessary, but I just wanted to make sure we weren't going to have any leaks. I wanted to give ample time for the bed liner and the caulking and everything to dry in between. And so that's why this has taken me some time. And in addition to that, I've been using the machine. And so I've been trying to fit in the repairs and upgrades with the jobs and trying to do that and bring you the videos as linear as possible. So we're doing our best over here. We have a lot more videos to come in this series. After this, we're gonna be doing some scraping on the new machine. We have some custom parts that we made. There's 3D printing, there's CNC machining. There's all kinds of stuff coming up in this playlist. So watch out for that. And until next time, we'll see you on the next one.